Hello everyone to this new episode of MRM Highlights. We are here today with Tonima S and Konstantin Momot from Queensland University of Technology in Brisbane. Their paper on transverse relaxation-based assessment of mammographic density and breast tissue composition by single-site portable NMR was an editor pick for September. Before I ask him a few questions to know more about their work, let's first have a look at their slides.
Today, we will present our work on transverse relaxation-based assessment of mammographic density and breast tissue composition by single-sided portable NMR. The credit of this work goes to the wonderful group of collaborators whose picture you can see here, which includes both students and professionals in the field of medical physics, cancer and cell biologists, clinical radiologists, and breast surgeons. This particular work is part of a project where we plan to aim portable NMR instrument for the mass and routine screening of mammographic density. This slide gives 4 examples of mammograms. Mammogram is the conventional method for assessing mammographic density. Here, the area that appears dark is the radiolucent adipose tissue, whereas the area that appears relatively bright is the radiodense fibroglandular tissue. In the population who has not been diagnosed with breast cancer can be categorized into 4 different classes or categories depending on the nature of the breast density-wise. We can see the women with BI-RADS 3 and BI-RADS 4 who has relatively dense breast and for the same reason relatively high risk of getting breast cancer, mammogram is not an effective method for them because of mammographic masking that can potentially hide or make it very difficult to find any abnormality in the breast tissue. For that reason, we propose the use of NMR-MOUSE, which uses the fundamental principle of MRI, which is not affected by mammographic masking. However, it's a desktop system which is not as expensive as MRI. It uses permanent magnets to create a horizontal magnetic field with constant vertical gradients, as you can see in this picture here. When the tissue sample is placed over the sensitive volume of this magnet, it allows a one-dimensional depth analysis, as you can see by the red line. For this experiment, we obtained breast tissue from women who underwent mastectomy or breast reduction surgery. A slice mammogram was obtained for each tissue slice that we used, and by a radiotherapist, the high mammographic density and low mammographic density regions were identified and outlined in the mammogram. Then, by comparing with the mammogram, we identified the regions with high mammographic density and low mammographic density in the tissue slice itself. After that, the tissue was placed on top of the sensitive volume of NMR-MOUSE, and using a CPMG sequence, which gives multi-slice multi-echo, we obtained a transverse relaxation decay. The parameters we used were 120 microsecond of TE, 10 second of TR, 4000 echoes, and 64 averages. After that, using inverse Laplace transform in MATLAB by using in-house code, we obtained T2 distribution histogram, as you can see in this picture here, where the x-axis shows all the T2 values present in this distribution and the y-axis shows the relative contribution of each T2 in the signal. First, we obtained transverse relaxation decay from the full slice samples as we have shown in the last slide. After that, the regions with high mammographic density and low mammographic density were excised, as you can see in this image here. The excised regions were placed on top of the NMR-MOUSE and a transverse relaxation decay was obtained for each sample. After that, these excised regions were soaked in deuterium oxide or heavy water for 16 to 18 hours to replace all the water inside the tissue with heavy water. After that, these samples were again placed on top of the NMR-MOUSE and a transverse relaxation decay was obtained in each case. When we analyzed the transverse relaxation decay obtained from a region with high mammographic density, we found that there were 2 distinctive peaks in the T2 distribution histogram, where one peak was centered near about 10 milliseconds and another peak was centered at about 100 milliseconds. On the other hand, After the same sample was soaked in heavy water and we obtained a transverse relaxation decay and we analyzed the transverse relaxation decay using inverse Laplace transform, in the T2 relaxation distribution, we only found one T2 peak, which was centered at about 100 milliseconds. Given that heavy water or deuterium is not responsive to NMR signal, we can conclude that this particular peak corresponds to fat. For the same reason, the other peak that's centered at about 10 milliseconds should correspond to water. We repeated the same analysis procedure for tissue regions with both high mammographic density and low mammographic density. In both cases, we found that after the tissue sample was soaked in deuterium oxide, there was only one T2 peak that were seen in the T2 distribution histogram, which corresponded to fat. Whereas when the tissue sample had water inside it, there were two peaks, one corresponded to water and the other corresponded to fat. The tissue with high mammographic density had a water peak which contributed to more signal in comparison to the tissue that had low mammographic density. In order to quantify these distributions, we measured two different parameters. One is geometric mean T2, which gives the average T2 for a peak for a logarithmic distribution, which is the case here. And the other one is area fraction, which gives us the relative proportion of the signal coming from one component, water or fat, in comparison to all the components present in the signal. Following the same analysis method, we repeated this analysis for all the samples that were used in the study, which were 9 samples altogether. We did this analysis for the tissue with high mammographic density, low mammographic density, samples from the excised slice as well as for the samples from the full slice. Then we plotted the geometric mean T2 and area fraction as we see in this figure. And by statistical analysis, it was shown that the area with high mammographic density can be clearly distinguished from the area with low mammographic density. Although the geometric mean T2 values were comparable, no matter what type of tissue it came from, but the area fraction was clearly different. And it showed that the analysis by NMR-MOUSE can not only differentiate between the high and low mammographic density, but it can also give us information on the relative composition of fat and water. And it is sensitive, it was equally sensitive for the slice that was taken from excised tissue and the slices that were taken from the full slice samples. Overall, NMR-MOUSE shows promise that it can be an effective platform for mass screening of mammographic density at a relatively cheaper cost and without involving ionizing radiation.
So to start off, could you tell us a little bit about yourself and how you became involved in MRI?
For myself, I just finished my PhD, so the paper that we will be talking about today was the last publication out of my PhD work.
Congratulations.
Thank you. I did my master's where I developed a software to look at MRI, and then during my PhD, I started to explore MRI in more details. So that's when, and I got in touch with Konstantin, and learned to do a lot more.
Mm-hmm. Well, I came to MRI by NMR spectroscopy actually, because I'm a physical chemist by training. I did my PhD in physical chemistry. And I spent a few years after my PhD just doing spectroscopic work, and then I gradually gravitated towards imaging. And I spent quite a few years doing imaging research. And I guess this portable NMR project is really a hybrid between spectroscopy and imaging, because it's got one-dimensional imaging capabilities, but it's also got characteristics of spectroscopy. So I guess in a way, this is coming back to spectroscopy, but via imaging.
And could you tell us how you became involved in this particular work?
We were interested to look into breast density, and given the situation at current clinical practice, it's usually done by X-ray mammogram, and it's good, but there are a lot of limitations that we have been talked about. It has been talked about in literature before, because it's a 2D projection of a 3D object, so there can be artifacts that can lead to misdiagnosis. And also the ionizing radiation is there. Doing MRI, we do know that it's safe, but that cost is very high for MRI. So we were looking for an alternative that could make a bridge between the two. And NMR-MOUSE was an excellent option because it's a desktop system, it's portable, it's relatively cheap. And we did some initial experiment and which looks good. And then we eventually went into look into breast density to explore that.
Could you tell us a little bit about the technical limitation in using an inverse Laplacian transform approach to reconstruct the T2 distribution?
Yes, of course. So that has been something we needed to look at in fair bit of details. We explored different methodologies because inverse Laplace transform, the basic algorithm is the same, but the software or the particular script that's used has been developed in different labs in different ways. So we chose the one that allows you to draw a curve that would plot the relative amplitude of the chi-square against the alpha. So when we're stumbled upon a relaxation distribution for NMR-MOUSE one, the particular advantage we had was there were a lot of relaxation data points, so it was relatively easy to do the analysis. But then when we are trying to find the minimum error using inverse Laplace transform, there always comes the issue of over smoothing it or under smoothing it or getting the right fit for that. And the trick was we always looked at the curve and we tried to find if it's a nearly L-shaped curve, so the bending point where it's a right balance between over smoothing it and under smoothing it. And initially, it was not very obvious which distribution we're getting to were correct. But then once we looked into more and more for the breast tissue that we were looking at, there's always a proportion of fibroglandular tissue and another proportion of fat there. So at the correct point when we chose it, we did see two different distributions. So sometimes when we would see a one bigger distribution, that would mean we are over smoothing it. On the contrary, if you'd see very sharp peaks where fat is absolutely separated from the FGD peak, that would mean that we are over smoothing it really. So it should the structure of it would tell us whether we are getting the distribution right or wrong.
Okay, well, as Tonima said, the inverse Laplace transform is quite sensitive to the smoothing parameter, the regularization parameter. And your inverse Laplace spectra, the T2 distributions do look quite different depending on what is the value of the regularization parameter that you use. But what we actually realized fairly recently is that when you just look at the relative areas of fat and water, the relative areas of the fat and water peaks, they're actually fairly insensitive to the exact value of the regularization parameter. So even if you slightly over smooth or slightly under smooth your inverse Laplace transforms, within a very wide range, it doesn't really affect the percentages of fat and water that you extract. So you'd have to massively undersmooth or oversmooth it for the answer to be wildly off. So I think it is actually a very good technique to use. I think it's very robust for what we're trying to achieve with it. So we're quite comfortable with quantifying the amounts of fat and water using inverse Laplace transform.
And were you surprised by the results?
For the results, when I looked at it for the first time, so just prior to this study, we did a study where we looked at the T1 of the same breast samples. For this one, when I started using inverse Laplace transform, I was not personally expecting such a big peak from the fat. And then our goal was really to try to find the diffusion effect on the value of T2, how it moves. But then we found that T2 was a much better marker. So I did look at this result a good number of times using different alpha values and different distribution, but it was really a very good technique. So, then I approached Konstantin, this is what I found, what do you think? And we just took it forward. And I think Konstantin is doing a lot more work on it now as well. Thank you.
Yeah, I guess the results were a little bit surprising initially because our initial mindset was that we were expecting to see the value of the T2 itself change with a relative fraction of fat and water. But if you look at the final figure in the paper, you actually see that the value of the T2 of fat and the T2 of water is fairly insensitive to the the relative amounts. So what we see is the change in the relative area of the fat and water peak, but not in the position of the fat and water peak in the T2 distribution. So it took us some time to change the mindset to go from expecting to see changes in the T2 to just analyzing the changes in the area fractions. And that's what we ultimately used for the analysis in this paper.